John Dalton in 1808 composed what is considered the first comprehensive atomic theory of matter. In his theory, Dalton attempted to explain the atomic nature of matter, but also what happens to these atoms when they undergo a chemical change. In his theory, Dalton said that all matter is composed of atoms, and that each chemical element is made up of its own type of atom, meaning that atoms of a given element were all identical in size, mass, and other properties, but also that atoms of different elements differed in size, mass, and other properties from one another. So all gold atoms were exactly like all other gold atoms, but unlike any other type of atom. And last, he said that all atoms are indivisible, meaning that they could not be broken into stable, smaller fundamental particles. Science has discovered a lot since the 1800s, so many of these are not considered to be true anymore. For example, atoms of a given element are not identical by mass. We know that there are isotopes, atoms of an element that have the same number of protons but different number of neutrons and therefore a different mass. And we also know sometimes two atoms of different elements can have the same mass. And most importantly, we know that atoms are divisible now. You can break them into their subatomic particles, the proton, neutron, and electrons. But to the best of our understanding, it's still considered that all matter is made up of atoms. And each chemical element is made up of its own type of atom, which is defined by the number of protons in that atom's nucleus. Dalton's atomic theory also describes about how elements combine to form compounds, as when elemental solid copper reacts with elemental oxygen in the air to form the compound copper 2 oxide. Dalton said that when elements combine to form compounds, they did so in simple, fixed, whole number ratios. This concept is known as the law of definite proportions. So when hydrogen and oxygen combine to form water, they always do so in a 2 atoms of hydrogen to 1 atom of oxygen ratio, and that is a fixed or defined proportion. This ratio holds true every time the elements combine, regardless of how much you start with. So if you have 4 atoms of hydrogen and 4 atoms of oxygen, you're still going to make water in a 2-to-1 ratio, but because you had extra oxygen, you'll have leftover oxygen. And if you had 6 atoms of hydrogen and 2 atoms of oxygen, you'll again still make your water in that 2-to-1 ratio, but you'll just be left over with extra hydrogen. Since a compound always contains the same elements, it always will have the same proportion of its mass be from those elements. We call this concept the mass percent. We can see here that 1 gram of CO2 or 16 grams of CO2 are always both going to be 72.7% oxygen by mass, even though 1 gram of CO2 has much less oxygen in it than 16 grams of CO2 has. They will both still have 72.7% of their mass be oxygen, because they're always 2 oxygen to 1 carbon, so as the mass of the carbon dioxide gets larger, the portion of the mass that is oxygen stays the same. But carbon and oxygen can come together to form a different compound, carbon monoxide. Interestingly, carbon monoxide is not 72.7% oxygen by mass, it is 57.1% oxygen by mass. And an easy way to tell 2 compounds that are made up of the same elements are different compounds is if they have different percentages by mass of their elements. Calculating mass percent is no more difficult than calculating any other percentage. We take the mass of the element in question, and then we just divide it by the mass of the compound, and then times it by 100 to make it a percent, a per 100. Just like any other percent, you take the part, you divide it by the whole, and you multiply it by 100. So in this example, we have 2 compounds that are both clear, colorless liquids that are made up of only hydrogen and oxygen. Are they both water, or are they different compounds? We can use percent mass data to see if they're the same compound. We take the mass of hydrogen in compound A, which is 3 grams, and divide that by 27 grams, the total, and multiply that by 100 to find that it is 11.11% hydrogen by mass. Doing the same for the oxygen in compound A, we see that oxygen is 88.89% of the mass. When we do the same calculations for compound B, we see that hydrogen makes up only 5.92% of the mass in compound B, which makes sense because 3 grams of hydrogen are in 50.62 grams of compound B. Since the percent hydrogen in these 2 hydrogen and oxygen only compounds are not the same, they cannot be the same compound. And they're not. Compound A is water. Compound B is actually hydrogen peroxide, not H2O, but H2O2. Dalton's atomic theory also reinforced that in chemical reactions, matter is not created nor destroyed. Simply, the atoms are rearranged to form new compounds from the existing compounds. We can see this when mass is conserved in a chemical reaction. For example, in this reaction, we start off with methane and oxygen, and the mass of methane and oxygen together is 80 grams. And after the reaction occurs, the atoms rearrange, so we end up with carbon dioxide and water. Yet the mass of that carbon dioxide is still 80 grams, because the atoms that were used to make the reactants are the same atoms used to make the products, just rearranged as you break chemical bonds and make new ones. If we look at the CH4, also known as methane, that we started with, 12 out of those 16 grams, or 75%, was carbon. And all of that carbon ends up in the CO2. So even though the CO2 that we make has only 27.3% of its mass is carbon, all 12 grams of carbon that started in the reactant side ends up in that CO2. You can see that no element changed the amount of mass present. They just changed where they're located and what percent of the compound they make up. So let's put this into practice. A student attempts to make magnesium chloride, which is MgCl2, according to the following reaction using 2.41 grams of solid magnesium and 7.29 grams of hydrochloric acid. The reaction results in 0.20 grams of hydrogen gas being released. What I'm asking here is determine the mass of magnesium chloride produced in this reaction. Well, we know that mass is conserved in a chemical reaction, so the sum of the products should equal the sum of the reactants. Since we started with 9.70 grams of reactants, we need to end with 9.70 grams of products. So that means our magnesium chloride must have been 9.50 grams. Magnesium chloride is 74.5% chlorine by mass. So is this product the student made magnesium chloride? Well, to know that, we need to do the mass of the element divided by the mass of the total compound times 100 to get a percent. So we need to know how much chlorine is in that compound. We know the total compound is 9.50 grams. To know the mass of chlorine, we got to think, well, where did the chlorine come from? The chlorine all came from the hydrochloric acid. And we actually know how much hydrogen is produced. We know that there's 0.20 grams of hydrogen. So that means that out of the 7.29 grams of hydrochloric acid we started with, 0.20 of it is hydrogen, meaning 7.09 grams of it must have been chloride. Given that matter is not created or destroyed in a chemical reaction, all of that chloride should have made its way into the magnesium chloride. So we take that 7.09 grams of chloride, and we divide that by the 9.50 grams of magnesium chloride, and we multiply that by 100 to make it a percent. And then we find that, yeah, we have 74.6% chlorine by mass, which is pretty much the exact same number with a little bit of a rounding error. So it's likely the student made magnesium chloride. While you can find the percent mass using lab data, it's actually easier if you have the periodic table and you know the chemical formula. Because when you know the chemical formula of a compound, you can use the average atomic mass values from the periodic table to determine the mass percent of that compound. So for example, we know the chemical formula of water is H2O. That means for every 1 molecule of water, we have 2 atoms of hydrogen, each with an average mass of 1.01 AMU, and 1 atom of oxygen with an average mass of 16.00 AMU. Since we have 2 of the hydrogen and 1 of the oxygen, they come together to be 18.02 AMU. We can use these values to determine the mass percent of each element. So since there's 2 hydrogen, we know that the total mass of hydrogen in the compound is 2.02. And since the total mass of the compound is 18.02 AMU, we just simply take 2.02 divided by 18.02, multiply that by 100, and we get the percent mass of hydrogen in water is 11.2%, exactly what we would expect. Doing the exact same math, but just for the oxygen this time, we would see that it would be 88.8% oxygen by mass. So now let's put this all together into one final problem. A student reacts iron with oxygen in the air to produce an iron oxide compound with an unknown formula. The teacher tells the student that the formula could be one of the 4 following: FeO, Fe2O, FeO2, or Fe2O3. Below is the student's lab data. So, given this lab data, what mass of oxygen must have reacted if you assume the law of conservation of matter to be true? We know that we had 1.19 grams of iron before the reaction, and we don't know how much oxygen reacted with it, but we know that the final product, the iron oxide, weighs 1.70 grams. So there must have been 0.51 grams of oxygen that reacted with the iron to make the iron oxide product. Before the student can figure out the chemical formula of the iron oxide, they need to know what was the percent oxygen by mass of the iron oxide they produced. So to do this, we take the mass of our oxygen, 0.51 grams, we divide it by the mass of our iron oxide, 1.70 grams, multiply it by 100 to make it a percent, and we find that we have 30% oxygen by mass. Now we simply have to match our lab data to one of the 4 possible compounds. So for each compound, we find out the total amount of iron in the compound, the total amount of oxygen in the compound, the total mass of the compound, and then we simply take the mass of the oxygen divided by the total compound times 100 to find the percent mass by oxygen in each compound. Matching the percentage we got from our lab data, which is 30%, to the percentage from these known values from the PR table, and we see that our compound was Fe2O3, since both had a 30% oxygen by mass.